Let's practice applying what you've learned with while loops and if-then conditionals in the following example. So here we have a function named greatest factor and a usage of it. On line 13, we're calling this function. I'd like to turn it over to you to try tracing through this using a memory diagram. So pause the video here and go ahead and trace through this. All right, so hopefully you were able to work through this. If not, this is some new syntax, so it's okay if you felt a little unsure of what to do at certain points. There are some important concepts conveyed in this particular example. First, at a high level, what we're doing in this example is writing a simple algorithm for finding the greatest factor of a number. So say a number like 15, what do we expect the greatest factor to be? This is the greatest number that will divide evenly into 15. As you know, hopefully through correctly tracing this, that'd be 5. Well, how does this algorithm work? Let's try stepping through it using a memory diagram. And we'll do this together. So I've got my stack and my heap, and I'll have my output over here. Right. And we're going to have globals. And in this example, our globals has a single entry in it that is greatest factor. ID 0. Let me make my heap a little bit smaller. We're not going to really have much going on in the heap in this example, so that's okay. So I'm going to make this over here, and now we've got ID 0 is the function lines 1 through 10. So this is a longer function. Notice our functions are getting longer as we start to add new tools of types of statements we can put inside of our statements, including variable declaration and assignment, if-then statements, and loops. So on line 13, we reach the call to greatest factor. And we see, okay, do we know what greatest factor is? Yes, it's this function. We've seen the definition for it. Does the parameter, does the argument n, which is being assigned an int, correspond to n, which is expecting an int input? Yes, it does. So let's go ahead and set this frame up. And hopefully these steps are starting to feel pretty comfortable at this point. There is most certainly a pattern to how all of this comes together. And the return address of this is line 13. That's where the call was occurred on. And n is the integer 15. But there's some machinery, there's some common steps. This is a very formulaic process. And it has to be in order to run a computer, because remember, a computer can only carry out a finite number of pretty simple steps. It just does it very rapidly. And so ultimately the number of different things we can do is pretty small, but because we've got a number of concepts coming together in an example like this, we have to be careful as we step through it. So now that we've established this, we go into the function body and we're in the frame. Our current frame is greatest function here on the stack, and the line that we're evaluating is line 2. Well, there's nothing to do here, so because it's a doc string. And then we, on line 3, reach a variable declaration and initialization statement. So we're declaring a variable named d of type integer, and we're assigning to it an initial value of n integer division 2. So what is n integer division 2? Well, n, we look up in our current frame, it's 15, so 15 integer division 2. Normally you would think this would be 7.5, right? But because it's integer division, we effectively just truncate or get rid of anything after the decimal point. That's the trick. Because in other words, this is 7 with a remainder of 1. If we were to do, what is 15? Let me actually do this here. What is 15 divided by 2? What's the remainder of that? This would be 1 because there would be 1 left over. So this value, d, is initialized to be 7. So we add d as a name in our current frame and assign it a value of 7. Fantastic. And then we reach a while statement. And here's the first time we are tracing together. How do we evaluate a while statement? So let's break this down. Well, when you encounter a while statement, it's this keyword while, and then what follows is its body, right? So this is the repeat block. We're only going to go into that repeat block when this condition evaluates to true. So let's try evaluating this expression here. This is a Boolean expression, so d greater than 1. We look up D in our current frame, that's 7. Is 7 greater than 1? Yes, of course it is. That's true. So we are going to enter our repeat block. And as soon as we do, we reach a print statement. Right? So our first printed statement is D colon, and then we substitute D because this is an F string, so D's current value in our current frame is 7. Great. And then we test if the remainder of dividing n by d is equal to 0. Well, let's break down. This is now an if statement, right? So now we're seeing the other piece of control flow syntax that we learned just recently. And this is yet again another Boolean expression. So these two constructs, the while loop and the if statement, share this in common. They have this Boolean expression that's this test. And they're testing whether or not we want to go inside of the block here. So the then block of this if-then statement is a single statement return D, right? But we only are going to do that if this expression evaluates true. So what is n? N is 15. And we actually already did this, 15, and then D is 7. We already did this. What is 15 divided by 7? What's the remainder of that if using integers? Well, this is 1. 1 is equal to 0 is false, right? So we do not go into the then block. We skip over it. This is one of the fundamental rules of an if-then statement. If the condition isn't true, you skip over the then. And if there were an else statement here, we would go directly into the else block. But notice there's not a matching else statement, so that's fine. You don't have to have one. And we continue on. And here we reach a variable assignment statement. And I'm actually going to remove this the repeat block. This is our variable assignment statement that we're working on. And we're saying, okay, remember, we always, when we reach this assignment operator, focus on the right-hand side. And the right-hand side is an expression, and in this case, it's D minus 1, so it's pretty simple, 6. 6 is being assigned to, remember that's how to read this single equal symbol. D is assigned 6, so D's value is no longer 7, it's now 6. Now here's where there's a big difference, the fundamental difference between an if statement and a while loop statement. So remember with this if statement, after we completed the then block or after we skipped over it, we just continued right on to the next thing. Well, that's not the case with the while loop, and where it gets its name from is once we've reached the end of this while loop, we go back up to the top of the while loop and we evaluate that condition again. And we're going to keep doing that same pattern of testing. Is this true? Okay, we're going to go into the repeat block. And then once we finish that repeat block, we go all the way back up. We test again. Is this still true? Yep. Okay. Go into the repeat block, test again. Eventually, hopefully, this becomes false. Otherwise, we might have something called an infinite loop, and our program won't stop unless you close your browser tab or shut down your program. So we go back up to the top, and now D is 6, and we test is 6 greater than 1. That's true. So we go into the repeat block and we print D colon, and the current value of D is 6, okay? And then we reach this test again, and here our test is now changed. We're testing 15 integer division 6. So what is 15 integer division 6? Well, remember 6 times 2 is 12, so that's the closest common factor between, or the closest way that we can divide 5 with 6. And then if we add 12, we would have 3 remainder, right? So the remainder of dividing 15 by 6 is 3. In other words, the way I always like to think about this is thinking about forming teams in sports. If you had teams of 6 and 15 people, you could form 2 teams. That would account for 12 people. And you have 3 people who weren't assigned to a team, right? So 3 is 3 equal to 0. And that's false, right? So we skip over the then block here. We skip over the then block, but we continue on, and we once again are decreasing D's value by 1. That's one way of thinking about this particular line of code. We're decrementing D by 1, but if we wanted to break it down step by step, we can. We take the current value of D at 6. 6 minus 1 is 5. 5 is assigned to D, so now D's value is updated. Well, we've once again reached the end of this while loops repeat block, right? So this is the repeat block. We know it because of this indentation. What do? Well, we don't go on to the next line. We go up to the top of this while loop and test this condition one more time. Is 5 greater than 1? That's still true. Okay, so now we go into the repeat block and we print D once more, D colon. And here we've got 5 is the current value of D. Cool. Let me make that a better 5. So 5 is the current value of D. And we test, is 15, what is the remainder of 15 divided by 5? Well, 0, right? 15 divides evenly by 5, so there's no remainder. So this would be 3 with 0 remainder. So this is now true. 15 divided by 5 has a remainder of 0. This evaluates to 0. So this would be 0. Is 0 equal to 0? Yes, that's true. So we go into the then block. And here we reach a return statement. What do we do with return? Well, if we look at our notes and that sheet that has our rules, what we would see is we first evaluate the expression, right? We always do that. So D, we look up D in our current frame. D is 5. So we're sending 5 back to our return address, line 13, and we need to enter it into this frame. So the return value is 5. We're just sending it back to line 13. We're sending it back here. And then because we've entered this return value and we're moving back to where we came from, this function jobs call is complete. And this is an important concept. So important that I want to pause and say this again. When we reach this return statement, because this condition became true, 5 did divide evenly into 15. That function's job is done. As soon as you reach, or as the process that's moving through the evaluation of a function reaches a return statement, that function call is over. We enter the return value and we send that return value back on to wherever we came from, our return address. Even if there are more lines that you could imagine, in fact, the very next line is this one, right? We would, if this weren't a return statement, we would have continued on to line 8. But because we hit a return statement, the semantics of a return statement are, once a return statement is evaluated inside of a function definition, you return that value straight back to the caller, and that function call is complete. It has nothing else to do. It solved this problem, and in this case, it did solve the problem. What is the greatest number we can divide 15 by without having any remainders? Well, 5, right? So, cool. So that brought us back to line 13, and then the last line of output here, because this function call did happen in the context of a print statement, would just be 5. All right. If you want to reason through another case of this, you can imagine dropping in a prime number here, like let's say 13. And 13 has no greatest factor other than 1, right? That's what makes it a prime number. And if you were to reason briefly through, what would happen here? Well, we would start with 6, right? Because we would take the integer division of 13 divided by 2. That would be 6.5 if we had a floating point, but we're saying an integer, so it's just 6 with a remainder of 1. So 6 is where we would start, and we would count all the way down. But once we reached a value where our D, which in this case it was short for denominator, I didn't want to have to write out numerator and denominator here, but hopefully you picked up on that. The denominator that we're dividing our numerator by n, this becomes 1. Well, every number is divisible evenly by 1. So this would become false. 1 greater than 1 is false. We would skip over the repeat block and we would return 1 in the case of 13. Now let's try playing with this. So I'm going to encourage you to actually try reproducing this example in your VS Code. This algorithm is called greatest factor. So if you want to pause the video here, start up your VS Code and enter create a new file named greatest factor, I'll encourage you to go ahead and get some practice writing an algorithm like this that makes use of both a while loop and an if statement. And notice we're combining those two. The if statement is inside of the while loop's repeat body. And we'll come back and explore this in Trailhead in just a moment. All right, so if I were to pull this up in Trailhead, what we'll see is the exact output we saw before. So this was D7, D6, D5, and 5. And I'm looking at my output column on my diagram, and it checks out. So our evaluation followed the same as the computers, which is what you would expect. Now, if I wanted to give that second example to you, we could try this with 13. So if I save this with 13, notice it does what we had described with words earlier. We start from 6 as the denominator. Nope, that's not evenly divisible into 13. 5 is not evenly divisible. 4 is not. 3 is not. 2 is not. So finally we reach 1. And we don't go into the repeat block when D is 1, because this becomes false. And when your condition becomes false, you skip over the repeat block and you go down and you continue on, and we reach a return statement here. So that would have caused that function called a complete. Now, notice how much faster this is. I change this to 15, I save it, boom, and we've computed that, which took us quite a few steps and a few minutes. In fact, we're on minute 15 right now to have done this by hand on pen and paper. But what if we tried something even bigger, like 15,151? What's the greatest factor of that? You'd be pretty frustrated with me if I asked you to produce a diagram for this particular example. Why? Well, let's try having the computer run this. So I save this file. And notice that we started at 7,575. And our algorithm says, okay, test that. Nope. That didn't divide evenly into 15,151. So we check the next item, 7,574. And there's, some lines hidden here. Trailhead's hiding some output from us. But if we expand that, notice how many numbers our computer was more than happy to test for us with this little algorithm that we wrote. We didn't change anything about our algorithm. All we changed was an input. But this algorithm is such that it's a sequence of steps that we carry out, and we apply some computational thinking, and our computer is more than happy to count down from 7,575 all the way down to 139, which who knew that would be the greatest common factor here. And if you wanted to drop another 0 on this, you can. Maybe I shouldn't do a 0. That was pretty easy, so we gave it an easy one. Let's drop an odd number here. And wow, look, we've tested 11,000 numbers at this point, and actually we could do this much faster if we weren't printing out the current value of D that we're testing as we move along. But notice our computer is more than happy to carry out tens of thousands, hundreds of thousands computations on our behalf. And this is one of the superpowers of computing. Now, I actually don't know how long this is going to go. So I've entered 151,000. We're up to 27,000. We would at most expect there to be 70,000 guesses. But if you find yourself in a place where, I don't really want this to continue going, all you need to do is navigate away from it, and your program will stop at that point. Or if you wanted to close your tab and open a new one, that would be fine. And you'll notice that if I were to open this again, it's actually going, it's still pretty slow. So I'm actually going to close that tab, and let's try this again. Let's see, greatest factor. Oops, localhost 1110. There we go. And we've started it again. So if you run into a situation where your program seems to be taking a long time, nothing's showing up, try closing your tab, reopening Trailhead in a new tab. Great work on this warm-up video.